Okay, so far we've only used the unit circle to find exact values of specific angles. However, we can also use it to find angles if we are being given a specific trig ratio, right? So what we mean by that is this, right? So far, we've only done things like what's sine of 30 degrees, and we've been able to give back 1/2. But now we can answer questions like this sine inverse of 1/2, which really means whose angle has a sine that is 1/2, right? Now, based on the unit circle, we know that one of the answers that is 30 degrees, right? Or, that's pi over 6, right? But we also know there's other places on the unit circle where we can get that answer, right? Sine is positive in quadrant 2. And so the sine of the 30-degree reference angle in quadrant 2 will also give you a value of 1/2. So, we can also have 150 degrees or 5 pi over 6 as well. And we can have lots and lots and lots of these different values, right? Same is true if we ask you to do something like find all possible values of cosine inverse of root 2 over 2. And how we read this is we're going to say, what angles have a cosine equal to this root 2 over 2, right? And what angles do have that? Well, we know that cosine in quadrant 1 would have a positive, would have an angle associated with positive root 2 over 2, right? And that angle would hopefully be 45 degrees or pi over 4, right? But then we know that cosine would be negative in quadrant 2 and quadrant 3 because it's only positive right here with the A and right down here with the C. So what would that 45-degree reference angle be in quadrant 4? Well, it would be 45 degrees away from 360, or basically 315 degrees, or 7 pi over 4. So now go ahead and try and answer this question. Find all possible values of tan inverse of 1, meaning what angles have a tan that equals 1? And the answers that would be 45 degrees and 225 degrees because tangent is positive in both quadrants 1 and quadrant 3. And when the sine and cosine are equal, which is at the 45-degree reference angles, that's when the ratio of them equals 1. All right, so these inverses that we've just been evaluating, the inverse of sine of 1/2, the inverse cosine of root 2 over 2, right? Are they functions? And hopefully the answer to that question is no, because they have more than one answer. In fact, we only listed 2 answers for each of them, but they could have an infinite number of answers because we could keep looping around that circle and coming up with the same values. So we can confirm this by looking at the functions, right? Here's our sine function. And how do we determine if the inverse of a function is also a function? And hopefully you remember we give it the horizontal line test, right? So if I get myself a horizontal line here and kind of have the graph, it's a little chubby of a horizontal line, but if we have it, we see it feels it all over the place. There's no way that our inverse is going to be a function. And this cosine one right here too, is this one a function? Is the inverse of cosine a function? Nope, it's definitely not. And the inverse of tangent a function? No, it is definitely not. So what we do is we try to isolate a part of each graph that we could kind of look at just a part of the graph rather than the whole thing and get it to pass this horizontal line test that we're trying to give it right here. And if we kind of look at that right here, the sine curve, right, we want it to pass the horizontal line test. So like this part of the sine curve passes the horizontal line test and gives us positive values. And now we're also going to need to be able to take inverses of negative values. So this part of the sine curve also passes the horizontal line test, right? If I only am looking at this one section of the graph, we will pass the horizontal line test. So we can make a portion of the graph pass the horizontal line test. How about cosine? Can we do the same thing? Well, yes, we just can't pick the same section, right? Here we went from, hopefully you know, negative pi over 2, where we get a value of negative 1, to positive pi over 2, right? And that's great. But if I went from negative pi over 2 on the cosine graph to positive pi over 2, I'd only be looking at this positive section of the cosine graph. So instead, we're going to start and we're going to look from 0 down to pi. Because from 0 down to pi will give us that positive section of the cosine graph and the negative section of the cosine graph, and it too now will pass the horizontal line test. For tangent, we have the same thing as we have the sine curve, right? We have this negative pi over 2 to positive pi over 2 gives us one complete tangent section that includes a negative part and a positive part and isn't somehow broken up by an asymptote. Because a lot of you might say, well, we could also use the same section as cosine, where we have a positive part and a negative part, but there's an asymptote in the middle, and not the value of 0, which is something we're going to want as well. So because more than one value of theta produces the same output for these trig functions, it's necessary to restrict the domain of each trig function in order to define the inverse trig functions. So, we can talk about inverse trig evaluations, but we can't talk about inverse trig functions if we leave them be. Trigonometric functions with a restricted domain are indicated with a capital letter. So sine, like we just said, the capital sine, the restricted sine function, is just like the sine function, except it's going to include only values between negative pi over 2 and pi over 2. So basically, that will be quadrant 1 and quadrant 4. The cosine function with a capital C, the restricted cosine function, is going to include only values in quadrant 1 and quadrant 2. And the tan function is only going to include values in quadrant 1 and quadrant 4. So here we have a chart, kind of it lays it all out for you, and it says the inverse sine function, capital S, inverse sine, where the sine of an angle equals a value. So if we take the inverse sine of that value, we can only get back values for the angle between negative pi over 2 and positive pi over 2, and so on. All right, so now when we go ahead and answer these questions, like what's the inverse cosine with a capital C of 1/2, there's only one answer that we can have, right? The angle whose cosine is 1/2 that only occurs between quadrants, I should switch that only occurs in quadrants 1 or 2. And the angle who has a cosine in quadrants 1 and 2, whose value is 1/2, is 60 degrees, or pi over 3. All right, try the other 3, and then join me back for another video.